Yesterday we showed you the heat, the records, the models that kept coming in too low. Today, the data got worse. The NWS office in Denver has stopped hedging. Their words, all-time March records will be broken again, by several degrees. Some of the numbers coming in this weekend would break summer records in March. But the temperature is not the part making climate scientists uncomfortable right now. What is making them uncomfortable is what is happening underneath the Pacific Ocean at the same time. The ENSO system is neutral. La Niña just collapsed. El Niño has not formed. The single most powerful amplifier of global heat is sitting in the off position, and the atmosphere is already doing this. Meanwhile, the subsurface data from the tropical Pacific shows a heat reservoir building at a pace that has forced model after model to revise upward, some now pointing towards Super El Niño territory by the end of the year. What you are watching this weekend is not the main event. It is what the atmosphere can do before the main event starts. Stay with me until the end, because the Pacific data we are about to walk through changes the context of everything on the temperature maps right now. If this has you hooked, subscribe to the Sky Lab, because the Pacific has not shown its hand yet, and when it does, we will be here breaking it down in real time. Leave a comment and tell us honestly, if this is what March looks like before El Niño arrives, what do you think winter 2026 looks like after it does? Now let's get into it. Part 1. This shouldn't be happening yet. Something is wrong with the calendar. That is the only conclusion a reasonable person can reach when confronted with what happened across the central United States in March of 2026. Denver, Colorado, a city where the normal high temperature in mid-March sits around 55 degrees Fahrenheit, hit 90 degrees. Not 89 point something, 90. That is not a warm March day. That is a hot June afternoon that somehow got lost and wandered into the wrong month entirely. And if Denver were alone in this, you could maybe chalk it up to a local oddity, a one-off atmospheric hiccup, something to mention at a dinner party and then forget. But Denver was not alone. It was not even close to alone. Across Kansas, soil moisture readings were collapsing into ranges that instruments typically associate with semi-arid desert conditions. The air was so dry that the standard metrics used to describe the Sahara were becoming relevant in the American plains. Grasses that should have been wet and tentatively green from late winter precipitation were already crackling. Farmers walking their fields in mid-March were describing conditions they normally do not see until August, if they see them at all. And meteorologists watching their data streams were doing something you almost never witness from professionals specifically trained to maintain composure in the face of ugly numbers. They were visibly shaken. 30 red flag warnings activated simultaneously across the plains. If that term is unfamiliar to you, a red flag warning is the National Weather Service telling you that the conditions for catastrophic wildfire are not approaching. They are here, right now, and a single spark in the wrong place could produce a fire that outruns every resource available to fight it. The formula is specific: low relative humidity, typically below 20%, sustained winds above 15 miles per hour, and temperatures high enough to continue drying out whatever moisture remains in the vegetation. These warnings normally begin appearing across the central states in late May. Having 30 active simultaneously in March is not a statistical outlier. It is a signal from a system that is no longer operating within its historical parameters. Here is where the story stops being merely extreme and starts being genuinely strange. We have explanations for anomalous spring heat. When the United States experiences warmth on this scale in late winter or early spring, there is usually a recognizable driver operating in the background. That driver is El Niño, a warming of the surface waters of the equatorial Pacific that rearranges global atmospheric circulation, displaces the jet stream, and tends to produce warmer and drier conditions across large parts of North America. Scientists know to look for El Niño when spring behaves like summer. They build its influence into seasonal forecasts. They warn agricultural communities months in advance. The system is imperfect, but it is consistent, and it gives forecasters a mechanism they can point to when the thermometers climb too high too early. El Niño was not present when this heatwave arrived. The equatorial Pacific was not in a warm phase. The planet had just finished a La Niña event, the opposite pattern, a cooling of those same Pacific waters, which typically acts as a moderating influence on global temperatures rather than an amplifying one. The atmospheric system was supposed to be in a cool, neutral or early transition state. Instead, it was producing heat that looked like the output of a climate operating a full season ahead of schedule. Think of it like arriving at a concert venue and finding the headliner already mid-set when the opening act was supposed to be sound checking. Something started without anyone giving it permission. Hundreds of weather stations broke all-time daily records during this event, and not by the kind of margins that make statisticians shrug. Some stations exceeded their previous March records by 8, 10, even 12 degrees Fahrenheit. To put that in context, a record broken by half a degree is news. A record broken by 12 degrees is a different category of event entirely. It is not the weather pushing slightly past what history said was possible. It is the weather ignoring what history said was possible and doing something else completely. The scale was not regional either. The anomaly stretched across multiple states, from the southern plains into the northern tier, affecting an area so large that calling it a local event would be like calling the Pacific Ocean a puddle. Scientists use a term that rarely escapes into public discourse: preconditioning. It describes a state where the baseline of a system is already elevated before the forcing that normally drives an extreme event has even engaged. The fuel is already laid, the kindling is already dry, the amplifier is still switched off, and if that is the situation we are in, if March 2026 represents a preconditioned baseline rather than a freak anomaly, then the question that follows is not comfortable. If this is what the climate system produces before its primary amplifier turns on, what does it produce when the amplifier engages? What does the rest of 2026 look like when the Pacific finally delivers what it is currently loading beneath its surface? That question does not have a reassuring answer. And to understand why, we need to look at what the statistics of this event actually reveal, because the numbers, when examined carefully, are stranger than the temperatures themselves. Or Part 2, the statistical shock. Most people hear the phrase all-time record broken and mentally file it alongside other weather superlatives. Hottest July ever, wettest November on record, that kind of thing. Records get broken constantly. The historical baseline grows by 1 year every year, the global temperature trend keeps nudging values upward, and records in a warming climate are expected to accumulate like interest in a bank account you did not ask for. Routine record breaking is real, it is significant, and it is worth tracking. But it is categorically different from what happened in March of 2026, and collapsing those two things into the same mental category is exactly how you miss the part of this story that should genuinely concern you. Climate scientists make a distinction between records that are broken and records that are shattered. The difference is not rhetorical, it is mathematical. When a temperature record falls by 1/10 of a degree or 1/4 of a degree, that is a record at the edge of the normal distribution, the tail of the bell curve doing what tails of bell curves occasionally do, which is producing a value slightly more extreme than anything previously observed. That kind of record is expected in a warming climate. What is not expected is a record that falls by 8, 10, or 12 degrees. That is not the tail of the distribution. That is a value that lives outside the distribution as it was historically understood. The bell curve did not predict it. The warming-adjusted bell curve did not predict it. Whatever produced it was operating outside the statistical framework built from decades of observations. The technical language for extreme deviation uses a unit called sigma, which is shorthand for standard deviation, a measure of how far a value sits from the average relative to the normal spread of the data. A 2 sigma event sits in roughly the top 2.5% of historical outcomes. A 3 sigma event is in the top 0.1%. During the March 2026 heat event, temperature anomalies across portions of the central United States were registering at 4 sigma, 5 sigma, and in localized areas, 6 sigma above the seasonal average. A 6 sigma event in a statistically stable system should occur roughly once in every 500 million years of observations. Obviously, the climate system is not statistically stable, and that specific return period does not literally apply. But here is the thing, the models we use to forecast climate already account for the instability. They already incorporate the observed warming trend. They already allow for the distribution to shift warmer over time, and the March observations still fell outside the model-predicted range, not outside the historical range adjusted for stability, outside the already warming-adjusted modern projection. Reality was exceeding the projection that had already been updated to expect a hotter reality. What elevated this event from remarkable to scientifically alarming was not any single station's reading in isolation. It was the clustering. Multiple extreme deviations happening simultaneously across an enormous contiguous area. The entire central United States, from the Texas Panhandle through Kansas, Nebraska, and into the Dakotas, was experiencing anomalies that individually would each warrant serious scientific attention. Together, they formed a pattern statisticians call co-occurrence, rare events piling up at the same moment in time and space. The probability of any one of these anomalies is low. The probability of all of them occurring simultaneously across the same region in the same week is so small that expressing it as a percentage requires scientific notation. It is not the kind of thing you explain by saying the dice happened to roll high. It is the kind of thing that makes you wonder whether the dice have changed. Climate scientists have been documenting a pattern over the past 2 decades that goes by the unglamorous name of asymmetric volatility. The idea is that the distribution of temperature outcomes is not simply shifting warmer, it is also changing shape. Cold extremes are becoming less cold at a moderate rate. Heat extremes are becoming more extreme at a faster rate. The distribution is developing what mathematicians call a fat tail on the warm side, a tail that extends much further from the average than a normal distribution would predict, meaning that events far from average are more likely than historical statistics suggest. A fat tail is dangerous not because the average is wrong, but because the average hides the risk that lives in the extremes. You can have a completely accurate forecast for a typical day and a catastrophically wrong estimate for the worst day of the year. The fat tail is where the damage lives, and the fat tail of the temperature distribution is getting fatter. There is one more piece of this statistical picture that deserves attention, and it is the piece that climate modelers have been discussing with increasing urgency in recent years. The gap between what models project and what observations report has been widening, and it has been widening in a specific direction. The average values are tracking reasonably well. The middle of the distribution, the typical weather on typical days, is behaving roughly as the models anticipated. But the extremes are outrunning the projections. The worst events are worse than predicted. The hottest readings are hotter than the model envelope. If you are the kind of person who finds comfort in the idea that scientists have this all mapped out, this is the detail that should give you pause. The models are already assuming things are getting worse. Things are getting worse faster than the models that assumed they would get worse. That is a sentence worth sitting with for a moment. Because if the statistics are breaking under conditions that have not even reached their anticipated peak, then the mechanism producing those statistics must be doing something beyond what we modelled. And that mechanism, the actual atmospheric machinery that turned March into June, is something the media described with a phrase that is technically accurate and deeply incomplete. Part 3, the heat dome wasn't the story. Every major outlet covering this event deployed the same 2 words, heat dome. It appeared in headlines, in television stand-ups, in social media posts from meteorologists who absolutely know better, but also need their graphics to make sense in 30 seconds. Heat dome is a useful phrase. It is visual. It conveys the basic physical reality that a mass of hot, stagnant air sat over the central United States and declined to move. But using heat dome as a complete explanation for what happened in March of 2026 is like explaining a warehouse fire by saying the warehouse was very warm, accurate, insufficient, and missing the entire interesting part. A heat dome forms when a ridge of high pressure builds in the upper atmosphere, specifically around the 500 millibar pressure level, roughly 18,000 feet above the surface. This ridge acts as a cap, suppressing the convective activity that would normally allow surface heat to vent upward. Air within the dome sinks, sinking air compresses, compressed air warms. The physics here are identical to what happens inside a bicycle pump when you push the handle down. The pump gets warm because you are squeezing the air molecules closer together and increasing their kinetic energy. Now imagine that process operating across several 100,000 square miles of the American interior simultaneously. The air above the plains was being squeezed toward the surface like a slow, invisible piston, arriving at ground level warmer than when it started. And the longer the dome sat in place, the more the surface heated, and the more the heated surface reinforced the conditions that kept the dome stationary. It was a self-sustaining oven. The 2021 Pacific Northwest heatwave is the modern reference event for what a truly exceptional heat dome can produce when everything goes wrong in the same place at the same time. Portland, Oregon reached 116 degrees Fahrenheit, a city whose previous all-time record was 107, which had itself seemed almost fictional before it was exceeded by 9 degrees in a single afternoon. Seattle hit 108. Hundreds of people died. The event shocked the scientific community not because heat domes were unknown, but because the magnitude of the outcome exceeded what anyone had modelled as plausible for that region at that point in the warming trajectory. That dome was the story because the dome itself was exceptional. The atmospheric blocking pattern was unusually intense, unusually persistent, and operated over a region with almost no adaptive infrastructure for extreme heat. The March 2026 event was different in a way that matters enormously for how we think about future risk. The 2021 dome formed over conditions that were relatively normal for late June in the Pacific Northwest. Cool, marine-influenced, moistened by the nearby ocean. It was extreme because the dome was extreme. In 2026, the dome formed over conditions that were already anomalously warm before the dome arrived. The soil was already dry. The air was already carrying less moisture than early spring should contain. The baseline temperature of the surface was already elevated above what seasonal norms would predict. The dome did not create the heat event. It amplified a heat event that was already underway. It was not the origin of the fire. It was a lid placed over a fire that was already burning, concentrating the heat that would otherwise have dispersed. This distinction carries real implications. If extreme heat domes are inherently rare and inherently extreme atmospheric configurations, then their damage is bounded by their rarity. You can plan around them, build resilience to them, and treat them as infrequent but survivable shocks to the system. But if heat domes are increasingly forming over an elevated baseline, if the surface they sit on is pre-warmed before they arrive, then even a modest dome becomes capable of producing outcomes that only an exceptional dome could have produced a generation ago. The dome does not need to be extraordinary if the ground it works with is already extraordinary. A blowtorch applied to soaking wet wood does limited damage. The same blowtorch applied to tinder-dry kindling is a different situation entirely. Researchers who study atmospheric blocking patterns have been tracking a signal that does not yet have a settled mechanistic explanation, but is increasingly difficult to dismiss. Blocking events, periods when the upper-level atmospheric flow gets locked into one configuration and resists the kind of disruption that normally reshuffles weather patterns, appear to be persisting longer than historical averages would predict. The leading hypothesis connects this to changes in the temperature gradient between the Arctic and the mid-latitudes. As the Arctic warms faster than the surrounding regions, the temperature contrast that drives the strong, fast, relatively stable jet stream weakens. A weaker gradient produces a slower, more meandering atmospheric flow that develops large amplitude waves, waves that are more prone to stalling. When the flow stalls, it stalls over wherever it happens to be. And whatever that region is experiencing, heat, cold, rainfall, drought, it experiences for longer. The March dome did not stall over the plains by accident. It stalled because the atmospheric configuration that promotes stalling has been occurring more frequently. But here is the thing, the dome was working with a surface that had already been primed to amplify whatever it produced. And understanding how that surface got primed requires going back to a process that began months before the heatwave arrived, and that operates not in the sky, but in the ground itself. Part 4. The land surface feedback loop is breaking models. The ground beneath the plains is not a passive recipient of whatever the atmosphere decides to deliver. That fact gets systematically underestimated in popular explanations of heat waves, and it has been systematically underestimated in climate models until relatively recently, which is part of why the models have been surprised by the magnitude of recent extreme heat events. The land surface is an active participant in the heat system, capable of amplifying or suppressing atmospheric warmth depending on its own state. In March of 2026, the land was in a state it had no business being in during early spring. It was behaving like the middle of August. Understanding why requires knowing about two categories of heat that meteorologists and physicists distinguish carefully. Sensible heat is what you feel. It is warmth as a tangible, thermometer-readable quantity, the heat that makes the air itself hot to breathe. Latent heat is different. It is the heat that gets absorbed or released during phase changes. When water transitions from liquid to vapor, for instance, it absorbs a significant amount of energy from its surroundings in the process. This absorption is why evaporation cools things. Your body produces sweat precisely to exploit this mechanism. The sweat evaporates. The evaporation absorbs heat from your skin, and you cool down. Plants do something similar through their stomata, and the land surface does it through a process called evapotranspiration. the continuous evaporation of moisture from soil and vegetation that converts incoming solar energy into water vapor rather than heat. In a moist environment, a substantial fraction of the sun's energy goes into driving evaporation instead of warming the surface. Wet soil is a natural air conditioner. It takes energy that would otherwise become heat and redirects it into a phase change instead. Dry soil does the opposite with merciless efficiency. When soil moisture is depleted, there is no water available to evaporate. The incoming solar radiation cannot be converted to latent heat because the conversion medium, liquid water, is not there. All of that solar energy becomes sensible heat instead. Every joule that the sun delivers to a dry surface goes directly into warming that surface and the air above it, with nothing redirected into evaporation. This is why deserts reach extreme daytime temperatures despite receiving no more solar radiation than more temperate regions. The absence of moisture means there is no competing process. The energy has one destination, and one destination only, which is heat. In a normal march across the plains, this mechanism does not matter much because the soil is not dry. Winter precipitation, snowpack, and the gradual onset of spring mean that surface moisture is relatively abundant entering the transition season. Evapotranspiration is limited not by lack of moisture but by lack of warmth. Temperatures are still too low to drive vigorous evaporation. The system is in a kind of stored readiness. The cooling mechanism is loaded. If anomalous heat arrives, the wet soil can partially buffer it by redirecting incoming energy into evaporation rather than surface warming. The natural air conditioner activates automatically when it is needed. What the Western United States experienced ahead of the March 2026 event was a winter of below normal snowpack across key accumulation zones. The snowmelt that would normally have recharged soil moisture through February and March did not materialize at expected volumes. Soils across portions of the central and southern plains entered March at moisture levels more characteristic of late summer conditions than late winter. The buffer was not loaded. There was almost nothing available for evapotranspiration to work with. When the heat dome arrived and solar radiation began flooding the surface, essentially all of it converted directly to sensible heat. The amplification was immediate. The temperatures climbed faster and further than they would have over normally moist spring soil. What makes this especially significant from a modelling perspective is the feedback loop it creates. Heat dries soil further. Dried soil generates more heat. More heat dries more soil. Climate models have known about this land-atmosphere coupling for decades, but repeated post-event analyses have found that its strength in real conditions consistently exceeds model assumptions. The coupling is tighter and faster than simulations predict. When coupling is underestimated, extreme heat events are underestimated. The model says 9 degrees above average. The thermometer says 14. The gap is not random error. It is a systematic consequence of getting the land-atmosphere interaction wrong. And the implications extend well beyond any single heat wave, because if early season soil dryness becomes a recurring feature of a warming climate, if winters deliver less snow and springs arrive without their historical moisture cushion, then every spring heat dome will begin its amplification from a more dangerous starting point. The feedback loop will engage earlier and run longer every year. The ceiling of possible March temperatures will keep rising, and there is one signal that tells you with brutal visible clarity when the feedback loop has pushed conditions past a threshold. You can see it from space. You can see it from your window. It is the thing that happens when dry grass meets wind and heat, and it is a signal that the entire atmosphere has been watching carefully. Part 5. The Fire Weather Signal. A red flag. Warning is the Weather Service's most serious fire risk alert, and it is issued with precision. The conditions required are specific: relative humidity below 20 to 25%, sustained winds above 15 to 20 miles per hour, and temperatures elevated enough to continue driving moisture out of vegetation and fine fuels. All three elements must converge simultaneously. Any two without the third is concerning. All three together creates what fire behavior scientists call a critically flammable environment, a state where ignition requires almost no provocation and where the resulting fire can spread faster than the resources designated to stop it can organize a response. Under full red flag conditions, fire behavior models routinely project rates of spread that outrun the operational capabilities of suppression agencies. This is not a failure of those agencies. It is a physical reality of what fire does in certain atmospheric states. 30 simultaneous red flag warnings across the plains in a single March day would have been considered nearly impossible to plan for in any operational framework built on historical precedent. The fire season across the Great Plains has traditionally run from late April through early October, with the most dangerous conditions concentrated in the June through August window, when temperatures are highest and humidity is lowest. Agency deployment schedules, equipment maintenance cycles, mutual aid agreements, and staffing models are all built around that historical window. The idea that full critical fire weather would arrive in mid-March, before seasonal hiring is complete, before equipment has cleared its winter maintenance cycle, before pre-positioning decisions have been made, falls outside the operational planning horizon that historical data would justify constructing. Until now, that planning gap was theoretical. In March of 2026, it was not theoretical anymore. What makes grassland fire in the plains particularly dangerous in ways that even experienced observers underestimate is the speed of spread. Forest fires dominate media coverage because they are visually dramatic, and because they threaten forested communities with high property values and high media access. But grassland fire is faster by an order of magnitude under the right conditions. A crown fire moving through forested terrain under extreme conditions might travel at 10 to 15 miles per hour. A grassland fire in 30 mile per hour winds can travel at 30, 40, or even 50 miles per hour. The math of that situation is unforgiving. If the fire is moving at the same speed as the wind driving it, and the wind is also the reason the evacuation routes are dangerous, then the buffer between ignition and catastrophe can collapse in minutes rather than hours. The plains have seen some of the most sudden and total losses of life and property in American fire history for exactly this reason. Events that received a fraction of the national attention of slower-moving forest fires but were in many ways more immediately lethal. The conditions that produce red flag warnings in March are not random atmospheric noise. They are the direct, visible, measurable output of the land surface and atmospheric processes we have been examining. The dryness is the soil moisture feedback in action. The wind is the atmospheric instability that comes with strong pressure gradients during anomalous heating. The heat is the heat dome amplifying a pre-warmed surface. Red flag warnings in March are not a separate phenomenon from the anomalous temperatures and the dry soils and the unusual atmospheric configuration. They are the same phenomenon expressed in a form that has immediate, practical, dangerous consequences. When you see 30 of them in March, you're not looking at a fire risk alert. You're looking at a diagnostic reading of the entire system. Fire ecologists and climate scientists studying the timing of fire weather have been documenting a shift that goes beyond the familiar observation that fire seasons are getting longer. The shift they are increasingly describing is structural rather than incremental. The concept is sometimes called seasonal compression, the idea that the period of genuinely moderate, low-risk transitional weather between the cold season and the hot season is narrowing. Winter and summer are not just getting warmer at their extremes, they're crowding out spring and fall as distinct climatic periods. The mild middle is shrinking. The dangerous ends are expanding toward each other. In some regions of the western and central United States, what was once a recognizable 2-month buffer of relatively fire-safe spring conditions before peak fire season has compressed into a window of weeks, or in some years, into essentially nothing at all. If fire season is already fully present in March, not approaching, not developing, but here, active, generating emergency responses across an area of the size of multiple European countries, then the question about summer is not rhetorical, it is operational. It is a resource allocation question, a public health question, a question about how emergency management systems that were built around a set of seasonal assumptions now function when those assumptions no longer hold. The fire weather signal in March of 2026 was not just an alarm for the event occurring in that moment. It was a canary delivering a message about the entire season to come. And to understand what that season might bring, we need to travel not to the sky above the plains or the soil beneath them, but to the surface of the Pacific Ocean, and then further to what lies beneath it. Part 6. The Pacific is charging. The Pacific Ocean is not a body of water. That categorization is accurate in the way that calling the sun a hot object is accurate. Technically correct and almost completely failing to convey the scale of what you are describing. The Pacific covers more area than all of Earth's landmasses combined. It contains more than half of the planet's liquid water by volume. It absorbs approximately 90% of the excess heat trapped by greenhouse gases in the atmosphere. It drives precipitation patterns, determines monsoon timing, shapes the jet streams of both hemispheres, and regulates global temperatures on timescales ranging from seasons to centuries. Understanding what the Pacific is doing right now is not an academic exercise. It is the most important variable in any serious projection of what the next 12 months look like for the planet's weather and climate. What the Pacific is doing right now beneath its surface is charging. The mechanism involves a layer of the ocean that sits between roughly 100 and 300 meters below the surface, below the mixed layer that interacts directly and rapidly with the atmosphere, but above the cold, slow, dense water of the true ocean deep. This zone is called the thermocline, and it functions as the ocean's thermal bank account. Heat absorbed at the surface can be mixed downward into the thermocline during periods of strong wind-driven mixing, where it is stored at depth rather than immediately released back to the atmosphere. This stored heat is not visible from satellites monitoring sea surface temperatures. It does not show up in the readings that drive most weather models. It sits below the surface, patient, accumulating, waiting for the oceanographic conditions that will allow it to rise. The Argo Float Network, a global array of roughly 4,000 autonomous robotic sensors that drift through the ocean at various depths and periodically surface to transmit their measurements, has been tracking subsurface temperature anomalies in the equatorial Pacific with increasing concern over the past several years. The volume of anomalously warm water between 100 and 300 meters depth in the equatorial Pacific has been growing. Not at the surface, where warming would immediately influence atmospheric conditions. Below it, heat that entered the ocean through the surface and was subsequently mixed downward has been accumulating in the thermocline at rates above historical norms. The thermal battery, to use the most fitting metaphor available, is not just charged, it is overcharged. It contains more stored energy than is typical for this phase of the climate cycle, and it contains more than the seasonal models, calibrated on historical averages, predicted it should. Why does this matter for what comes next? Because the mechanism that releases thermocline heat into the atmosphere has a name, and that name is El Niño. Under normal Pacific circulation, trade winds blowing from east to west pile warm water in the western Pacific and drive cold water upwelling along the coast of South America. The thermocline in the eastern Pacific sits relatively deep. The surface temperatures in the eastern Pacific are cool because the cold water is continuously being brought up from below. When the trade winds weaken, for reasons that are still not fully understood in terms of their ultimate trigger, that warm water sloshes eastward. The thermocline rises in the east. The accumulated heat stored below the surface is suddenly close enough to the top to interact with the atmosphere. Sea surface temperatures in the central and eastern Pacific climb rapidly. The atmosphere above them warms. Atmospheric circulation patterns reshape globally. An El Niño event has begun. The battery is discharging. The critical variable in determining how powerful that discharge will be is how much was stored before the discharge started. A larger thermal reservoir in the thermocline before El Niño onset means more energy available for the atmosphere-ocean coupling to work with. It means a longer potential duration for the event. It means a stronger potential surface warming signal. And the Argo data going into the spring of 2026 was showing a thermocline heat content that was exceptional by historical standards. The conditions preceding the strongest El Niño events in the observational record, including the two that climate scientists use as their benchmark comparison events, were, in terms of subsurface heat accumulation, not dramatically different from what was being observed in the Pacific in early 2026. This is the kind of statement that sounds technical and dry until you understand what the benchmark events it is being compared to actually produced. And to understand that, we need to look at what happened the last two times the Pacific discharged a reservoir this large, because those events reshaped global weather in ways that are still being studied decades later. Part 7. The collapse of La Niña was too fast. Climate systems are supposed to have inertia. That is not a metaphor imported from physics for rhetorical effect. It is a literal physical property rooted in the enormous heat capacity of the ocean and the timescales over which large water masses change temperature. A fully developed La Niña event does not switch off. It decays. The process takes time, months of gradually weakening trade winds, slowly diminishing cold water upwelling in the eastern Pacific, progressive warming of the sea surface temperatures that had been suppressed during the cold phase. Historical records show that the typical La Niña event takes somewhere between 6 and 12 months from its peak intensity to return to neutral conditions. This decay timeline is predictable enough that seasonal forecast models use the state of a decaying La Niña as a meaningful input for projections extending 6 to 9 months into the future. The system changes slowly, and that slowness is information. The La Niña that preceded the events of 2026 did not follow this script. Its decay was compressed. Where models had projected a gradual transition over the standard 6 to 12-month window, the observed cold anomalies in the equatorial Pacific collapsed on a timeline that was shorter than the historical average, significantly shorter. Sea surface temperatures in the eastern Pacific that had been running below normal during the La Niña phase returned to neutral and then began climbing toward above normal values at a rate that outpaced the seasonal forecast guidance. The transition happened faster than expected, and in a system where the rate of change is itself a source of predictive information, a faster than expected rate of change is not just an inconvenience for forecasters, it is a signal that the system is behaving differently than the historical record taught us to expect. The reason rapid transitions matter goes back to a property of complex coupled systems, the overshoot effect. Think of a pendulum. A pendulum that swings slowly has time to approach equilibrium smoothly at each extreme before reversing. A pendulum that is pushed abruptly past its equilibrium position does not stop at neutral. It swings through and overshoots on the other side, producing a larger amplitude oscillation than the initial push alone would have generated. Climate transitions between La Niña and El Niño can behave analogously. A rapid collapse of La Niña can drive an atmospheric overshoot, a period where the atmosphere, which had been configured around the La Niña circulation state, finds itself abruptly without the oceanic driver that was organizing its patterns. The atmospheric circulation does not instantly find a new equilibrium. It oscillates. It produces anomalies that are not cleanly explained by either the ending La Niña or the not yet established El Niño. It generates weather events that exist in the gap between the two states, and that gap in early 2026 appeared to coincide precisely with the March heat wave. Transition instability is a recognized concept in ENSO research, ENSO being the El Niño Southern Oscillation, the broader climate pattern that includes both El Niño and La Niña as its opposing phases. But it is historically difficult to forecast because it depends on the rate of change rather than just the current state of the system. A model calibrated on historical transition timescales may not adequately capture the behavior of a transition that is occurring faster than any historical analogue, and this is where a pattern that researchers have been flagging becomes relevant. The ENSO cycle, the back-and-forth swing between warm and cold Pacific conditions, appears to be operating on shorter timescales than the historical record established as typical. The transitions are becoming more abrupt. The time spent in stable phases appears to be decreasing. The swings are sharper. Whether this reflects a genuine shift in ENSO dynamics driven by background warming or represents natural variability at the unusual end of the historical range remains an active scientific debate. But the possibility that the climate system is losing some of its characteristic inertia, that it is responding faster, transitioning more abruptly, and spending less time in stable states, is exactly the kind of change that would produce the atmospheric behavior we observed in March. A system with less inertia is a system that surprises you more often, and in a warming climate, the surprises tend to run hot. But the most important consequence of the rapid La Niña collapse was not the atmospheric instability it produced during the transition. It was what it left behind in the Pacific, specifically the state in which it delivered the ocean to the conditions preceding the next phase. Because what was building beneath the Pacific surface as La Niña ended was something the models could not agree on, and that disagreement itself was a warning. Part 8. Are we heading toward a super El Niño? In the Northern Hemisphere spring of 1997, oceanographers monitoring the equatorial Pacific began noticing that the numbers were moving in an unusual direction. Sea surface temperatures in the central and eastern Pacific were rising faster than seasonal models predicted. Subsurface heat content readings from the limited monitoring network available at the time showed anomalies that were well above historical norms. Trade winds were weakening, and their weakening was feeding back on the ocean warming, which was feeding back on further wind weakening, in a self-accelerating loop that the data showed no signs of interrupting. By the summer of 1997, it was clear that a major El Niño was developing. By autumn, it was clear this was not a routine event. By the peak of the event in the Northern Hemisphere, winter of 1997 to 1998, global average surface temperatures had spiked to the highest level in the instrumental record to that point. Floods devastated parts of South America and East Africa. Drought gripped Indonesia and Australia. Coral reefs bleached across the tropics. The 1997-98 El Niño set the benchmark for what a maximally powerful expression of this climate phenomenon could produce. Then, almost 2 decades later, it happened again. The 2015 to 2016 El Niño matched, and by some indices exceeded its predecessor. Models in early 2015 were detecting the same precursor signatures that had preceded the 1997-98 event: exceptional subsurface heat content, rapid eastern Pacific warming, weakening trade winds. By winter of 2015 to 2016, the global temperature record was broken again. The phrase Super El Niño entered widespread usage. Climate scientists who had spent their careers telling students that no 2 El Niño events are identical found themselves writing papers comparing 2 events that were, in terms of their intensity and precursor conditions, almost uncomfortably similar to each other. What both events shared, in retrospect, was not just exceptional peak intensity, they shared an exceptional build-up phase. In both cases, the subsurface heat content in the equatorial Pacific before the event began was well above the average for years preceding a typical El Niño. The thermocline was loaded before the atmospheric coupling started. The battery was overcharged before the discharge began. This relationship between precursor subsurface heat content and eventual El Niño intensity is not a perfect predictor. The atmosphere has to cooperate. The wind anomalies have to develop and sustain themselves. There are atmospheric Kelvin waves and oceanic Rossby waves and coupled feedbacks that can amplify or dampen an incipient event in ways that are not fully predictable months in advance. But the precursor heat content is the best single physical variable for identifying when a very strong event is possible, as opposed to merely probable. The subsurface heat content readings in the equatorial Pacific in early 2026 were, by the Argo float measurements, exceptional. Comparable in magnitude to the precursor conditions that preceded the benchmark strong events. Model guidance for the El Niño that was developing was widely divergent, and that divergence was itself a signal. When seasonal forecast models agree closely on an El Niño forecast, it usually indicates a moderate event with well-constrained dynamics. When they spread widely, with some projecting a moderate event and others projecting a strong to very strong event, it indicates high sensitivity to initial conditions and to processes that different models represent differently. The forecast spread for winter 2026 to 2027 was large. The tail of the model distribution extended into territory that, if realized, would produce global temperature anomalies comparable to the 2 benchmark events. Whether that tail scenario would verify was genuinely uncertain, but the possibility could not be dismissed. There is one additional factor that makes a potentially strong El Niño in 2026 more consequential than a comparable event would have been in 1997 or 2015. The background warming trend has continued. The baseline global surface temperature against which an El Niño signal is added is higher now than it was during either of the 2 benchmark events. El Niño does not warm the planet independently, it temporarily amplifies whatever the current background temperature already is. In 1997, El Niño was being added to a background roughly 0.4 degrees above pre-industrial levels. In 2026, that background is approximately 1.5 degrees higher. The same magnitude El Niño signal added to a warmer starting point produces absolute temperatures that are higher than any previous event of equivalent relative intensity. Records that the 1997-98 event set by narrow margins could be exceeded by wider margins by an event of equivalent relative strength occurring now, simply because the floor is higher. This is not speculation, it is arithmetic, and the arithmetic, when applied to the subsurface heat data coming out of the Pacific, produces numbers that make the March heat wave look, in retrospect, less like an outlier and more like a preview. Part 9. The jet stream is acting out of season. There is a river of wind circling the planet at approximately 30,000 feet. You cannot see it. You cannot feel it from the ground. But you interact with its consequences every single day of your life, whether you're aware of it or not. This river determines where storms track and where they do not. It determines which regions experience warmth and which experience cold in any given week. It shapes the path of hurricanes, governs the timing of monsoons, dictates whether your winter is mild or brutal, and establishes the invisible boundaries between the air masses that define what we call regional climate. It is called the jet stream, and most people go their entire lives benefiting from its behaviour without once thinking about it. Which is fine, honestly. It is the kind of relationship that works best when you do not have to think about it. The problem is that in the spring of 2026, the jet stream started doing something that made atmospheric scientists think about it constantly. And the phrase that kept appearing in their internal communications with unusual frequency was this: it was acting out of season. The jet stream is driven by temperature contrasts. Not surface temperatures, not the air you breathe at ground level, but the contrast between the large air masses that occupy different latitudinal zones of the planet. Specifically, it is powered by the temperature difference between the cold, dense air masses sitting over the Arctic and polar regions, and the warmer, lighter air masses of the mid-latitudes below them. This contrast creates a pressure gradient, and that gradient drives the fast, concentrated river of upper-level wind that we call the jet stream. The physics are the same as what drives any wind. Air moves from high pressure toward low pressure, and the greater the contrast, the faster the movement. A large temperature contrast produces a strong, fast, tightly constrained jet. A reduced temperature contrast produces a weaker, slower, more loosely organized one. This single relationship, temperature contrast driving jet stream strength, is the key to understanding almost everything that followed in March of 2026. A strong, fast jet stream has a characteristic behavior pattern that is enormously beneficial for the region sitting beneath it. It tends to flow in a relatively straight west to east direction across the northern hemisphere, with moderate undulations that carry weather systems through a region and then move them along. Think of it as a conveyor belt that keeps the atmospheric deck shuffling. Weather patterns arrive, do their thing for a few days, and then get swept downstream by the next disturbance riding the jet. This is why a heat wave in a strongly driven atmosphere tends to last a few days and then break. The jet stream brings the next frontal system through, cooler air follows, the temperatures drop, and people go back to complaining about ordinary weather. The jet stream, when it is strong and moving efficiently, is one of the planet's most effective natural thermostats. It prevents any single regime from sitting in place long enough to become catastrophic. A weak jet stream does the opposite. When the driving temperature contrast diminishes, the jet slows, and its flow develops larger amplitude waves, bigger north-south meanders that swing further toward the equator on their southward dips, and further toward the pole on their northward surges. These large amplitude waves move more slowly than the tighter waves of a strong jet. They propagate westward more sluggishly, and they are significantly more prone to what meteorologists call blocking, a state where the upper-level atmospheric pattern essentially locks into a fixed configuration and resists the kind of perturbations that would normally force it to evolve. A blocked pattern can persist for days or weeks over the same location. Whatever the blocked pattern is producing, heat, cold, rain, drought, it produces it continuously, without interruption, until the block finally breaks down. Blocking events are associated with some of the most damaging weather extremes in the historical record. The 2003 European heatwave that killed tens of thousands of people was a blocking event. The 2010 Russian heatwave was a blocking event. Extended blocking is not rare, but blocking of unusual amplitude and unusual persistence is a different matter. Arctic amplification is the mechanism that connects global warming to jet stream behavior, and it is worth understanding in some detail because it is central to one of the most consequential and contested debates in current atmospheric science. The Arctic is warming faster than the rest of the planet, roughly 2 to 4 times faster than the global average, depending on the season and the specific region measured. This differential warming rate is a well-documented observation, not a projection. It shows up consistently across multiple independent datasets covering surface temperatures, ocean temperatures, sea ice extent, and atmospheric soundings. The physical reasons for it involve several reinforcing processes, including the loss of reflective sea ice that exposes dark ocean water to solar absorption, changes in atmospheric heat transport from lower latitudes, and feedbacks involving water vapor and clouds that operate differently at high latitudes than elsewhere. The Arctic is warming fast, that part is settled. The contested part is what that warming does to the jet stream. The Arctic amplification hypothesis sometimes called the wavy jet stream hypothesis, proposes that as the Arctic warms faster than the mid-latitudes, the temperature contrast that drives the jet stream decreases. A decreased contrast weakens the jet. A weaker jet develops larger amplitude waves. Larger amplitude waves block more easily and persist longer. Therefore, extreme weather events driven by atmospheric blocking become more frequent and more prolonged as Arctic warming accelerates. This chain of reasoning is physically coherent and theoretically well motivated. It is also genuinely disputed. Some researchers have published analyses finding strong statistical support for increased blocking frequency in the observational record. Others have published equally rigorous analyses finding that the signal is not statistically distinguishable from natural variability, given the length of the available record. The scientific debate is real, the uncertainty is honest, and anyone who tells you the question is fully resolved is either misrepresenting the literature or has a very confident book to sell you. What is not disputed is what the jet stream was doing over North America in March of 2026. The upper-level flow was characterized by what meteorologists call amplified ridging, a pronounced northward bulge in the 500 millibar height field over the western and central United States. This ridge was not subtle. Its amplitude was unusual for March. The degree to which it displaced the climatological westerly flow poleward was unusual for March. Its persistence, the number of consecutive days it maintained a similar configuration without the kind of shortwave disturbance that normally reshuffles upper-level patterns every 5 to 7 days, was unusual for March. The atmospheric flow was locked. The ridge sat stationary over the central continent like a geological feature rather than a meteorological one. The heat dome that formed beneath it had nowhere to go because the upper-level flow that would normally carry it away was not moving. And underneath that stationary dome, the temperatures climbed day after day, without the relief that a moving, active jet stream would have delivered. People waited for the break. The break did not come. The ridge that locked over North America in March was not a mystery in the sense that its presence was unexplained. Meteorologists could see it, track it, and describe its structure in detail. What was harder to explain was its unusual amplitude and its unusual persistence for that time of year. March is not a month when the atmospheric flow typically supports strong, stationary blocking over the central United States. The temperature contrast between the Arctic and the mid-latitudes in March is normally still substantial enough to drive a relatively active, progressive jet stream. The fact that the March 2026 ridge defied this expectation, that it formed with greater amplitude and lasted longer than seasonal norms would predict, is consistent with what the Arctic amplification hypothesis says should happen as the polar temperature contrast weakens. Whether it proves that hypothesis is a different question. A single event, however dramatic, does not prove a long-term trend, but it is data. It is a data point in a direction, and the direction it points is toward a climate system where the atmospheric conveyor belt that prevents any single extreme from lasting too long is running slower, meandering more, and stalling more easily than it used to. There is a practical consequence of all of this that extends beyond any specific heat wave. If the jet stream is genuinely becoming more prone to large amplitude blocking patterns, then the duration of extreme events increases across the board. Not just heat waves, also cold outbreaks, floods, droughts, and any other weather regime that produces its damage through persistence rather than peak intensity. The March 2026 heat wave was extreme, partly because it was hot. It was also extreme partly because it lasted. The combination of unusual temperature and unusual duration is what pushed the agricultural and fire impacts into historic territory. A jet stream that produces more of those combinations more often, at higher baseline temperatures, is a jet stream that is fundamentally changing the risk profile of living in the mid-latitudes. And that change is happening alongside every other change this investigation has been examining: the elevated ocean temperatures, the loading Pacific, the Antarctic sea ice retreat, the active solar cycle. Each of these systems is operating at its own level of anomaly. But they are not operating independently of each other. They are interacting, they are coupling, and some scientists, looking at the full picture of what the data shows, have begun asking a question that is harder to answer than any of the physical ones. Not what mechanism is producing these anomalies, but whether there are mechanisms the models are not seeing at all. Part 10. The phantom forcing problem. Science is most comfortable when it can account for everything. When the numbers add up cleanly. When the known causes produce the observed effects within a margin of error that feels manageable, that sits inside the uncertainty bounds the models declared in advance. There is a particular satisfaction in that kind of accounting, not just aesthetic satisfaction, though that is real, but practical satisfaction, because a model that accounts for everything is a model you can trust to tell you what comes next. Climate science has spent decades building toward exactly that kind of trustworthiness, and it has largely succeeded. The models that project global temperature change in response to rising greenhouse gas concentrations have proven broadly correct in their directional assessment. They predicted warming, the planet warmed. They predicted sea level rise, the seas rose. They predicted more frequent and intense heat extremes. The extremes arrived. This is not a small achievement. It represents the accumulated effort of thousands of researchers across multiple continents and multiple generations, working with instruments and computational tools that improved with each passing decade. The foundational climate science is solid. That needs to be said clearly before the next sentence, because the next sentence is where the discomfort begins. In recent years, the models have been underestimating. Not across the board, and not in every variable, but in specific areas, particularly in the behaviour of extremes. The gap between what the models projected and what the observations reported has been widening in a consistent direction. The average temperature values are tracking reasonably well. The middle of the distribution, the typical weather on typical days, is behaving roughly as expected, but the tails are running hotter than predicted. The worst events are worse than the model envelope suggested they should be. The most extreme readings are landing outside the projected range, and the honest scientific response to a systematic gap between projection and observation is not to defend the projection. It is to ask what the projection is missing. That question, what are the models missing, is one of the most actively investigated and genuinely unsettling questions in current climate science. And the candidates that have emerged to answer it are not exotic or theoretical. They are real physical processes that are known, studied, and included in the models. The problem is that their magnitudes are uncertain, and some of them may be operating at the more aggressive end of their plausible ranges, in ways the model ensembles did not anticipate. The first candidate involves aerosols, and it is worth understanding in some detail, because its implications extend well beyond any single heatwave or any single year. Aerosols are tiny particles suspended in the atmosphere, produced by combustion, industrial processes, dust, sea spray, and a range of natural and anthropogenic sources. They interact with solar radiation in two primary ways. First, they scatter incoming sunlight, reflecting some fraction of it back to space before it reaches the surface and warms it. Second, they act as condensation nuclei around which cloud droplets form, and when more nuclei are present, clouds tend to form with more but smaller droplets, which increases their reflectivity. Both effects produce cooling. Aerosols in aggregate have been acting as a partial offset to greenhouse warming for as long as industrial civilization has been emitting them. The magnitude of this offset is one of the largest sources of uncertainty in climate sensitivity estimates. Large enough that the Intergovernmental Panel on Climate Change has consistently listed aerosol forcing as among the least well-constrained terms in the global energy budget. In 2020, the International Maritime Organization implemented new regulations requiring a dramatic reduction in sulfur content in marine shipping fuel from 3.5% sulfur to 0.5%. The shipping industry is one of the largest single sources of sulfur dioxide emissions globally, and sulfur dioxide is a primary precursor to the sulfate aerosols that have the strongest cloud brightening effect over the ocean. The regulation was implemented for entirely legitimate public health reasons. Sulfur emissions from ships were causing measurable harm to coastal populations and marine ecosystems. The air quality benefits were real and significant, but the climate side effect of removing a large aerosol source is that the cooling offset it was providing gets removed with it. If sulfate aerosols from shipping had been masking a meaningful fraction of greenhouse warming over the world's oceans, then their rapid reduction would unmask that warming abruptly. The ocean surface temperatures would climb faster than the trend established during the decades of high aerosol shipping. And beginning in 2023, global sea surface temperatures began climbing faster than trend in a way that multiple research groups have proposed may be at least partly attributable to exactly this mechanism. The causal attribution is still actively debated. The timing is uncomfortable to dismiss. Cloud feedbacks represent a second area where the models may be getting the magnitude wrong in a direction that matters. clouds are simultaneously one of the most important and one of the least well-modelled components of the climate system. Their effects on the surface energy budget are large. Globally, clouds reflect enough solar radiation to cool the surface by roughly 50 watts per square metre, while simultaneously trapping enough outgoing infrared radiation to warm it by roughly 30 watts per square metre. The net cooling effect of about 20 watts per square metre is larger than the total forcing from all greenhouse gases emitted since the Industrial Revolution. Small changes in cloud cover, cloud altitude, or cloud optical properties can therefore produce large changes in the surface energy budget. The question for climate projections is not what clouds do today, but how they change as the planet warms and the models do not agree. Different climate models, using different parameterizations of cloud microphysics and convective processes, produce cloud feedbacks that range from modestly negative to significantly positive. The spread in equilibrium climate sensitivity across the model ensemble, the range of long-term warming expected from a doubling of carbon dioxide, is largely a function of this cloud feedback disagreement. Recent analyses of satellite observations of reflected solar radiation have suggested that the net cloud feedback may be tracking toward the positive end of the modelled range, meaning that cloud changes as the planet warms are amplifying warming rather than dampening it. If that tracking is correct and sustained, it implies a climate sensitivity closer to the high end of current estimates. A higher climate sensitivity means faster warming for the same emissions trajectory. It means the models that have been used to set policy targets may be underestimating how quickly the forcing translates into temperature change. Ocean heat uptake efficiency is the third major candidate, and it connects directly to some of the ocean circulation anomalies that other parts of this investigation have examined. The rate at which the ocean absorbs excess heat from the atmosphere is not fixed. It depends on the circulation patterns that move surface water downward and replace it with cooler water from below, effectively pumping excess heat into the ocean interior, where it is sequestered away from the atmospheric temperature record. The Southern Ocean, the band of ocean circling Antarctica, has historically been the most efficient heat absorber in the global system, responsible for a disproportionate fraction of total ocean heat uptake. Changes in Southern Ocean circulation driven by shifting wind patterns, freshwater input from melting ice, and altered density gradients may be reducing its uptake efficiency. Similar concerns apply to portions of the North Atlantic. A less efficient ocean heat sink means that a larger fraction of the excess energy trapped by greenhouse gases stays in the atmosphere rather than being drawn into the ocean. The atmospheric warming rate accelerates for the same emissions forcing. The gap between what the models projected and what the thermometers report widens in exactly the direction that has been observed. What connects these three candidates, aerosol reduction, cloud feedbacks, and ocean heat uptake efficiency, is not that they are unknown or poorly studied. They are included in every major climate model. They are researched extensively. The problem is that each of them carries a range of plausible magnitudes, and if any one of them, or some combination of all three, is operating at the more aggressive end of its plausible range, the combined effect could account for a substantial portion of the observed gap between model projections and recent observed warming. Scientists have an informal term for this collection of underestimated but real drivers. They call them phantom forcings. The name is not meant to imply anything supernatural or conspiratorial. It simply captures the situation accurately. These are forcings that are present in the observational record, visible in the data, producing measurable effects in the real world, but that appear too weak or are missing entirely in the model output. They are invisible in the projections while being present in the measurements. They are the gap between the map and the territory. And the March heat wave, when viewed through this lens, is not just an extreme weather event in a warming world. It is a data point produced by a system operating at a higher effective forcing than the models predicted. A system where the phantom forcings may be filling in the gap between what the greenhouse gas trend alone would produce and what the thermometers are actually recording. The implications of phantom forcings for near-term risk assessment are significant and not particularly comforting. If the gap between projections and observations is systematic rather than random, if there are real physical processes consistently pushing the warming faster than the central model estimate, then planning and adaptation frameworks built around the central model estimate are systematically underestimating the pace of change. The targets set to limit warming to specific thresholds may be more difficult to meet than the models suggest, not because the targets are wrong, but because the timeline is compressed. The safety margins built into infrastructure design agricultural planning, and emergency management frameworks may be thinner than assumed, and the events that the projections classify as tail risks, rare, extreme outcomes at the edge of the model distribution, may be arriving on timescales that make them operationally relevant much sooner than projected. The March heatwave was one of those events. It was not supposed to be possible in March, and it was not happening in isolation. It was happening on a planet where every ocean basin was simultaneously showing temperature anomalies without historical precedent, where the poles were losing stability faster than projected, and where the forcing that normally explains spring heat extremes had not even engaged yet. The phantom forcings do not explain everything, but they may explain the gap between the world the models described and the world the instruments are measuring, and that gap in the spring of 2026 was no longer small enough to ignore. Part 11. Oceans are breaking records everywhere. The planet is approximately 71% ocean by surface area, and that simple geometric fact is the most important number in any serious discussion of how the Earth's climate system actually operates. We think of ourselves as living on a terrestrial planet because we are terrestrial creatures. We stand on land, we build on land, we measure weather at land-based stations, and we intuitively experience the world through the filter of our own solid footing. But the ocean is not the background of the climate system. It is the system. It is the primary reservoir of heat, the primary driver of atmospheric moisture, the primary moderator of temperature extremes, and the primary sink for the excess energy that greenhouse gases trap near the surface. When climate scientists talk about where the heat from global warming actually goes, the answer is not the atmosphere. The answer, overwhelmingly, is the ocean. Roughly 90% of the excess energy accumulated by the Earth system since the Industrial Revolution has been absorbed by the world's oceans. The atmosphere got the headlines, the ocean did the work, and for decades, that arrangement moderated the pace of surface warming in ways that made the changes feel gradual enough to debate, gradual enough to defer, gradual enough to treat as a distant problem. That arrangement is changing. And the evidence that it is changing has been accumulating across every ocean basin on the planet simultaneously, in a pattern that has pushed oceanographers from professional concern into something that sits closer to the other end of that emotional spectrum. To understand what a marine heatwave is and why its recent behaviour is significant, you need a working picture of what the ocean normally does with the energy it receives. The ocean absorbs solar radiation at its surface and distributes that energy through several mechanisms. Surface currents driven by wind move warm water laterally, from the tropics toward the poles, transferring thermal energy across thousands of miles of open water. Thermohaline circulation, the density-driven overturning circulation that operates on timescales of centuries to millennia, moves water vertically, carrying heat downward into the ocean interior and bringing cold, dense, nutrient-rich water back toward the surface in upwelling zones. The ocean exchanges heat and moisture continuously with the atmosphere above it through evaporation and sensible heat transfer, and this exchange moderates temperature in both directions. Coastal regions sitting adjacent to cold upwelling zones are cooler than their latitude would otherwise predict, because the ocean is constantly drawing frigid water from depth and exposing it at the surface. Regions bathed by warm ocean currents are warmer than their latitude would predict for the opposite reason. The Gulf Stream keeps northwestern Europe habitable at latitudes that, without it, would produce climates comparable to northern Canada. The ocean is not passive geography. It is the active thermal infrastructure of the planet, and its behaviour sets the boundary conditions within which the atmosphere must operate. A marine heatwave is defined with technical precision. Sea surface temperatures in a given region must exceed the 99th percentile of the historical average for that location and that time of year, and they must maintain that exceedance for 5 or more consecutive days. This definition was developed to identify genuinely anomalous events, not warm seasons, not above-average years, but conditions so far outside the historical norm for a specific place and time that they constitute a distinct physical state with distinct ecological and atmospheric consequences. Under this definition, isolated marine heatwaves have been documented in the observational record for decades. The Northeast Pacific experienced a notable one between 2013 and 2015, a sprawling mass of anomalously warm water that disrupted fisheries, drove toxic algal blooms along the Pacific coast, and altered atmospheric circulation patterns across the western United States. That event was studied intensively and treated as an exceptional occurrence, a warning of what marine heat waves could look like under future warming scenarios. It was not supposed to be a preview of routine conditions. What began shifting around 2023 was not the existence of marine heat waves, but their geographic scale, their simultaneity, and their persistence. The North Atlantic Ocean's surface temperatures in the summer of 2023 ran at levels so far above the historical record that the anomaly graphs being circulated among oceanographers looked, to outside observers, like data errors. They were not data errors. The North Atlantic was running at temperatures that exceeded the previous record by margins large enough to be unambiguous across multiple independent datasets. The Indian Ocean showed persistent above-normal anomalies through the same period. The Southern Ocean, which has historically functioned as the most efficient heat absorber in the global system, responsible for a disproportionate share of total ocean heat uptake relative to its surface area, showed surface temperature departures that confounded the researchers who had spent careers studying it. And these basin-level anomalies were not occurring in sequence, one after another in a pattern that might suggest a travelling disturbance or a propagating mode of variability. They were occurring simultaneously. Multiple ocean basins in different hemispheres, with different circulation systems and different seasonal cycles, were all running above their historical records at the same time. The global mean sea surface temperature, averaged across all basins, climbed to levels that the models had not projected until later in the century, under the emissions scenarios that were actually being followed. The planet's ocean was running decades ahead of schedule. The physical mechanism connecting warmer ocean surfaces to the atmospheric behaviour we have been examining throughout this investigation is direct and well established. The ocean surface is the lower boundary condition for the atmosphere. The atmosphere develops its temperature structure, its moisture content, its stability characteristics, and its circulation patterns in response to the surface it sits on. A warmer ocean surface provides more energy to the atmosphere through evaporation. Warmer water evaporates faster, loading the atmosphere with more moisture, which carries latent heat that gets released when that moisture condenses into clouds and precipitation. A warmer ocean surface also reduces the temperature difference between the ocean and the lower atmosphere, which changes the efficiency of sensible heat transfer and alters the development of surface pressure patterns. Storm tracks shift, precipitation patterns reorganize, the thermodynamic environment for atmospheric convection changes. A warmer ocean is not simply a warmer ocean sitting passively beneath an unchanged sky. It is a fundamentally different lower boundary that forces the atmosphere to respond with different circulation patterns, different storm behaviour, and different temperature distributions than it would produce over cooler water. The March heat wave over the central United States did not occur in isolation from the anomalously warm ocean surfaces surrounding the North American continent. It occurred in an atmospheric environment that had been preconditioned by those ocean surfaces over weeks and months preceding the event. The buffering role of the ocean in the climate system deserves particular attention because it is the mechanism that explains why surface warming has been relatively gradual compared to what the total accumulated energy forcing would produce if it all stayed in the atmosphere. The ocean's enormous heat capacity and its ability to transport heat downward into the interior have absorbed approximately 90% of excess warming energy, effectively acting as a brake on atmospheric temperature rise. This buffering has been operating continuously since industrialization began loading the atmosphere with greenhouse gases. But buffering capacity is not infinite, and it is not static. A warmer ocean surface is less capable of absorbing additional heat at the same rate, for reasons that are physically straightforward. Heat flows from warm to cool. The larger the temperature difference between two objects in thermal contact, the faster the heat transfer. As the ocean warms, the temperature difference between the ocean and the atmosphere decreases, and the rate of heat transfer from atmosphere to ocean slows. The sponge analogy is imperfect, but useful. A dry sponge absorbs water rapidly, a saturated sponge absorbs it slowly, and a sponge that has been absorbing water continuously for 2 centuries is somewhere in between, with its absorption rate declining as its capacity fills. The ocean is not saturated, it has enormous remaining capacity in its cold interior waters. But the surface layer that exchanges heat with the atmosphere is warming, and that warming is reducing the efficiency of the primary mechanism by which the climate system has been moderating atmospheric temperature change. Less efficient ocean buffering means more of the excess energy stays in the atmosphere. More energy in the atmosphere means faster warming, more extreme heat events, more persistent blocking patterns, more anomalous March temperatures in Denver. The chain of causation runs continuously from the ocean surface to the thermometer in Colorado, and every link in that chain is now operating under conditions that have moved outside the historical range. The ecological consequences of record ocean temperatures are severe and well documented, though they receive less attention than the atmospheric effects that directly impact human infrastructure. Coral reef systems, which support roughly 25% of all marine species despite covering less than 1% of the ocean floor, bleach and die when water temperatures exceed their thermal tolerance by even 1 or 2 degrees Celsius for sustained periods. The Great Barrier Reef has experienced mass bleaching events of increasing frequency and severity. Tropical Pacific reef systems have seen bleaching on scales that researchers describe as ecosystem-level restructuring rather than temporary stress events. Fisheries dependent on cold upwelling zones have seen productivity disruptions as thermal stratification increases and upwelling weakens. Marine food webs are reorganizing as species distribution shift poleward in response to warming surface temperatures. These ecological changes are not footnotes to the physical story. They are the physical story expressing itself in biological form, the ocean warming signal translated into species distributions, food web structure, and ecosystem function. And the ecological disruptions feed back into the human systems that depend on ocean productivity for food security, coastal protection, and economic activity. But the ocean surface anomalies, as extraordinary as they are, represent only part of what the monitoring systems are detecting. Because at the planet's poles, particularly the southern one, the changes being observed are of a different character entirely, and they are being described by researchers who have spent decades studying polar systems using a word that, through overuse, has almost lost its capacity to communicate what it actually means. Part 12. Antarctic Sea Ice. Collapse is rewriting expectations. Antarctica is not the Arctic. This distinction matters enormously and is routinely collapsed in popular coverage of polar change, which tends to treat any news about melting ice at either end of the planet as interchangeable and equivalent, as though the poles are simply mirror images of each other, and what happens at one end of the Earth is roughly the same story as what happens at the other. It is not the same story. The Arctic is an ocean surrounded by land, the Antarctic is a continent surrounded by ocean. That geographic inversion produces fundamentally different ice dynamics, different feedback mechanisms, different relationships to global atmospheric and oceanic circulation, and different implications for the climate system as a whole. Conflating them is not just imprecise, it is the kind of imprecision that leads to genuinely wrong conclusions about which changes matter most, which timescales are relevant, and which thresholds, once crossed, cannot be uncrossed. The Antarctic story is its own story, and in recent years that story has taken a turn that researchers who have dedicated entire careers to studying the southern polar system describe with a consistency that itself carries meaning, as outside the range of anything the observational record prepared them to see. The sea ice that forms around Antarctica each winter and retreats each summer operates on a seasonal cycle, driven by the southern hemisphere's relationship to the sun. Ice extent reaches its annual minimum in February, at the end of the austral summer, when months of solar radiation have melted back the previous winter's growth. It reaches its maximum in September, at the end of the austral winter, when months of cold and darkness have allowed new ice to form and spread across the surrounding southern ocean. This cycle repeats every year, and across the satellite record that began in 1979, it repeated with enough regularity to establish a statistical baseline, a range of expected minimum and maximum extents, a sense of how much year-to-year variability was normal, and a framework for identifying when a given year's values were unusual. Antarctic sea ice was variable. Some years ran high, some years ran low. Unlike the Arctic, where the decline in sea ice extent over the satellite era is dramatic, statistically unambiguous, and visually striking on any graph that displays the data honestly, the Antarctic showed a trend that was genuinely complicated. There were periods of above-average ice extent. The linear trend through most of the record was weak enough that researchers argued seriously about whether a real trend existed at all, or whether the variability was simply masking whatever signal the warming background was trying to produce. The scientific community was cautious. The data supported caution. Drawing strong conclusions from a noisy record of limited length is exactly the kind of thing careful scientists avoid. Then 2023 happened. The February 2023 Antarctic sea ice minimum was not just low. It was categorically, historically, almost incomprehensibly low relative to the baseline the satellite record had established. The previous record minimum, set in 2022, had itself been notable. The 2023 minimum did not approach the previous record from below and nudge it downward by a modest margin. It demolished it. The gap between the 2023 minimum and the second lowest value in the satellite record was so large that the second lowest value looked, in context, like a normal year. Researchers accustomed to seeing records broken by incremental margins were confronted with a departure that forced them to reconsider the statistical framework they had been using to characterize Antarctic sea ice variability. A value that far outside the previously observed range cannot be fully explained by the kind of natural variability that produces ordinary record breaking. Something had changed. The debate was no longer about whether the signal existed. The debate shifted to what was producing it and whether it would persist. The persistence question answered itself with uncomfortable speed. The winter of 2023, the period when Antarctic sea ice should have been growing back from its record low February minimum toward a September maximum, failed to recover as expected. The growth was suppressed. The September 2023 maximum was the lowest on record. For the first time in the satellite era, the Antarctic sea ice failed to recover significantly from a record low minimum during the subsequent growth season. The following year showed similar suppression. The winter of 2024 produced another below normal maximum. By 2025 and into 2026, the pattern had persisted across multiple seasonal cycles, long enough that researchers who had maintained appropriate caution about attributing the initial anomaly to anything beyond natural variability were beginning, one by one, to revise their public assessments. A 2-year anomaly can be variability. A multi-year pattern of persistent suppression that survives multiple seasonal cycles is a different category of observation. It is the kind of observation that makes scientists update their priors. The most immediate physical consequence of reduced Antarctic sea ice involves a property called albedo, the reflectivity of a surface expressed as a fraction of incoming solar radiation that gets bounced back to space rather than absorbed. Fresh snow and sea ice have very high albedo values, reflecting roughly 80 to 90% of incoming solar radiation. Open ocean has a very low albedo, absorbing roughly 90 to 95% of incoming solar radiation. When sea ice retreats and is replaced by open ocean, the surface transitions from highly reflective to highly absorptive. The same solar radiation that would have been sent back to space by ice is instead absorbed by the dark water surface and converted to heat. This is a positive feedback. Warming melts ice. Melted ice exposes dark ocean absorbs more heat causes more warming melts more ice. The feedback loop runs continuously once it is engaged, and the only thing that interrupts it naturally is the return of winter darkness, which stops the solar input and allows new ice to form. When the winter recovery is itself suppressed, when new ice forms more slowly and to lesser extent than historical norms, the feedback has less interruption. The albedo loss accumulates across multiple seasons rather than being partially reset each winter. The magnitude of the albedo feedback from Antarctic sea ice loss is smaller per unit area than the equivalent feedback in the Arctic, because the sun angle at high southern latitudes is lower during the austral summer, meaning each square meter of ice to ocean transition absorbs less solar radiation than the same transition would at Arctic latitudes during northern summer. But Antarctica is large, and the sea ice zone that forms and melts around it each year covers an enormous area. Even at lower solar angles, the total additional solar absorption associated with the observed sea ice loss represents a meaningful addition to the global energy budget. Not a dominant forcing in isolation, but a real one, and one that adds to the other forcings being discussed throughout this investigation. Every additional watt per square meter of absorbed solar radiation that results from reduced Antarctic sea ice is one more contribution to the already elevated baseline that produced the March heatwave without El Niño's assistance. The deeper concern, the one that operates on longer timescales but carries far larger potential consequences, involves not the sea ice itself but what the sea ice protects. The Antarctic ice sheet is the largest single mass of frozen water on Earth, containing enough ice to raise global sea levels by approximately 58 meters if it melted entirely, which it will not do on any timescale relevant to current civilization. but even a partial and gradual destabilization of portions of the ice sheet would produce sea level rise that would reshape coastlines, displace hundreds of millions of people, and permanently alter the geography of human civilization. The West Antarctic ice sheet is the portion of this system that climate scientists watch most anxiously, and for a specific physical reason. Unlike most of the East Antarctic ice sheet, which sits on bedrock above sea level, the West Antarctic ice sheet is a marine ice sheet. It rests on bedrock that sits below sea level, sloping downward away from the coast toward the interior. This geometry creates a potential instability. When warm ocean water reaches the grounding line, the point where the ice sheet meets the ocean, it melts the base of the ice from below. As the grounding line retreats inland along the downward sloping bedrock, it exposes progressively more ice to ocean contact, which accelerates melting, which retreats the grounding line further, which exposes more ice. The feedback is self-reinforcing and, beyond a certain threshold, potentially irreversible on human timescales. The ice sheet itself is not in runaway collapse right now. The process of potential destabilization operates over decades to centuries, but the preconditions, warm ocean water reaching the ice margins, reduced sea ice buttressing, reducing the structural support for outlet glaciers, elevated ocean temperatures around the Antarctic margin, are becoming more consistently present in the observational record than they were a decade ago. The sea ice around Antarctica serves a mechanical function for the ice sheet that is separate from its albedo role and less widely understood. Floating sea ice and ice shelves act as a buttress, a structural support that resists the flow of land-based glaciers and ice streams toward the ocean. When that buttress is reduced or removed, the glaciers behind it accelerate. The relationship has been observed directly in cases where ice shelves have collapsed. The glaciers they were restraining sped up measurably within years of the collapse. Reduced sea ice extent by exposing more of the ice shelf margins to wave action and warm water intrusion increases the vulnerability of the buttressing ice shelves to the kind of fracturing and breakup that accelerates glacier flow. The connection between what is happening at the sea ice margin and what happens to the ice sheet interior is not hypothetical. It is a documented physical relationship operating in a system that is now experiencing the most anomalous sea ice conditions in the satellite era. None of this means catastrophe is imminent. What it means is that the margins of safety that separated the current state of the West Antarctic ice sheet from the threshold of self-sustaining instability are thinner than they were, and the observational signals that would precede a crossing of that threshold are becoming more consistent with what the monitoring systems are actually recording. The polar system is sending signals. The question of whether those signals represent a temporary excursion from a stable baseline or the early stages of a structural transition is one the next decade of observations will begin to answer. And while that question was developing at the bottom of the world, a different kind of energy input was quietly increasing from above, one that most people associate with climate denial arguments, but that carries a real, if modest, physical significance that deserves honest accounting. Part 13. The sun isn't helping. Every 11 years or so, the sun cycles through a period of increasing and then decreasing magnetic activity, and this rhythm has been ticking away in the background of Earth's climate system for as long as the sun has existed. At solar minimum, the sun's surface is relatively calm. Sunspots are sparse, solar flares are infrequent. The emission of energetic particles into the solar wind is reduced. The total amount of radiation arriving at the top of Earth's atmosphere sits at the lower end of the cycle's range. At solar maximum, the character of the sun changes noticeably. Sunspots proliferate across the solar disk in numbers that can be tracked with a simple telescope. Solar flares, sudden intense releases of electromagnetic radiation from magnetically active regions on the solar surface, erupt with regularity, sometimes several times per week. Coronal mass ejections, which are large expulsions of magnetized plasma from the sun's outer atmosphere, travel through the solar system at speeds of hundreds to thousands of kilometers per second, occasionally interacting with Earth's magnetic field and producing geomagnetic storms that disrupt satellite operations, radio communications, and power grids, while simultaneously generating the auroral displays that light up polar skies in curtains of green and red. And the total solar irradiance, the total energy output of the sun integrated across all wavelengths, increases modestly by a fraction of a percent compared to solar minimum values. This cycle has been tracked since the early days of telescopic astronomy. Galileo observed sunspots. The periodicity of the cycle was established in the 19th century, and its influence on Earth's climate has been studied with increasing sophistication for decades, using everything from ground-based solar observatories to space-based radiometers that measure total solar output with precision that earlier generations of astronomers could not have imagined. The conclusion of that extensive research is consistent across methods and research groups, and it needs to be stated clearly before anything else is said about the solar cycle's relevance to the events of 2026. The solar cycle is real. Its effects on the Earth system are measurable, and its contribution to the warming observed over the past century is small, genuinely, unambiguously, quantitatively small, compared to the forcing from greenhouse gases. This is not a contested finding. It is one of the most robustly established results in the attribution literature, and it is important to say so directly, because the solar cycle has a complicated history in public discussions of climate change, having been deployed repeatedly as an alternative explanation for observed warming in ways that the data simply do not support. The solar cycle has an amplitude of roughly 0.1% variation in total solar irradiance over its 11-year period. The warming produced by the accumulation of greenhouse gases since industrialization is approximately equivalent to the energy forcing that would result from a 1 to 2% permanent increase in total solar irradiance. That is 10 to 20 times larger than the entire amplitude of the solar cycle. You cannot explain a 1 to 2% forcing with a 0.1% variable. The arithmetic is straightforward and the conclusion is firm. Anyone telling you that solar variability explains the observed global warming trend is either unfamiliar with the quantitative literature or is choosing to ignore it. But having established that clearly, the opposite error is also worth avoiding, because it leads to a different kind of mistake. Dismissing solar variability as entirely irrelevant to near-term climate on the grounds that it cannot explain the long-term trend is an overcorrection that throws away real physical information. The solar cycle cannot explain the century-scale warming. It can contribute to year-to-year and decade-to-decade variability. It can add a small but non-zero forcing on top of other forcings. In a climate system that is already running at an elevated baseline, in a year when multiple other forcing factors are simultaneously pushing in the warming direction, a small additional solar contribution does not need to be large to be meaningful. It needs only to be real and to be pointed in the same direction as everything else. A stacking factor does not have to be the dominant term to change the sum. If you're carrying a heavy load and someone adds one more weight to it, the significance of that weight is not determined solely by its mass. It is determined by the state of the person carrying it. Solar Cycle 25, the current cycle, which began at solar minimum around late 2019 and early 2020, has been more active than the forecasters who specialize in solar cycle prediction initially expected. This is worth dwelling on because solar cycle prediction is a genuine science with a reasonable track record, and the forecasting community's assessment going into Cycle 25 was specific and quantitative. The prediction, based on several independent methods including geomagnetic precursor techniques and models of the solar dynamo, was for a relatively modest cycle, perhaps comparable in strength to Cycle 24, which had been one of the weakest solar cycles in a century. The forecast called for a solar maximum sunspot number in a range that would place Cycle 25 among the quieter cycles of the modern era. The actual observations have, consistently and by meaningful margins, exceeded this forecast. Sunspot counts began outpacing the predicted trajectory in the early ascending phase of the cycle and have continued to do so. The monthly smoothed sunspot number, the standard metric for characterizing solar cycle strength, was running above the predicted range by a margin that revised the cycle's expected peak intensity upward significantly from the initial forecast. Solar flare frequency has been elevated above what the cycle prediction implied. The number of significant geomagnetic storms produced by coronal mass ejection impacts has exceeded what a modest cycle would be expected to generate. In May of 2024, Earth experienced one of the most intense geomagnetic storms in 2 decades, a sequence of coronal mass ejection impacts that produced auroral displays visible at latitudes as far south as the Mediterranean and the southern United States, disrupted satellite operations, and briefly affected power grid stability in some regions. This was not the behavior of the quiet cycle that had been predicted. Solar Cycle 25 was running vigorous, and it was running ahead of schedule. The timing of the solar maximum matters for its climate relevance. Solar cycles do not produce a single sharp peak and then immediately decline. The maximum is a period of elevated activity that can span several years, with the highest sustained activity occurring over a window that typically runs 1 to 2 years around the peak. The initial forecast had placed the peak of cycle 25 somewhere in the range of 2025 to 2026. The actual development of the cycle suggested the peak was arriving earlier and running stronger than predicted, meaning that the period of maximum solar forcing on the Earth system was overlapping with a period when every other major climate forcing factor was simultaneously elevated. The elevated baseline from accumulated greenhouse warming, the anomalous ocean heat content, the reduced aerosol cooling from shipping regulation changes, the potential cloud feedback trending positive, the Southern Ocean heat uptake anomalies, and now, layered on top of all of these, an unexpectedly active solar maximum arriving ahead of schedule and delivering more total solar irradiance than the models calibrated on the forecast cycle strength had assumed. The additional warming contribution from an above-average solar maximum over a multi-year period is quantifiable within a range, and that range sits on the order of a few hundredths to perhaps a tenth of a degree Celsius of additional global mean surface warming compared to what a week cycle would produce over the same period. That is small in absolute terms. It is not zero, and in the context of a global mean temperature that in 2025 and 26 was already running at or near the 1.5 degrees Celsius threshold that international climate agreements had treated as a guardrail, a few hundredths of a degree in additional forcing is not academically trivial. It is the difference between a year that stays just below a symbolic threshold and a year that crosses it. It is one more contribution to the elevated baseline that was already producing anomalous March temperatures in Denver before El Niño had even engaged. It is, as the most accurate framing available describes it, a stacking factor, one more weight placed on the same side of a scale that was already carrying more than the projections expected. There is a particular irony embedded in the solar story that deserves a moment of acknowledgement, given the history of the public debate about climate change. For decades, solar variability was invoked by those skeptical of greenhouse gas attribution as the more likely explanation for observed warming. The scientific community responded correctly by showing that the solar contribution was too small to explain the observed trend. And that response was right. But the consequence of that debate was a cultural tendency in some climate communication circles to treat solar variability as essentially irrelevant to contemporary climate discussion, to dismiss it so thoroughly as a spurious alternative explanation that its genuine, modest, real contribution to near-term forcing variability got lost in the dismissal. The sun is not causing global warming. The sun is also not doing nothing. In 2026, it is doing slightly more than the forecast expected, at a moment when the system it is warming had already accumulated more heat than the models predicted. Every forcing that points in the same direction as every other forcing matters, even if its individual contribution is small. And just as the physical science community was working through the full inventory of these stacking forcings, the greenhouse gases, the aerosol reductions, the cloud feedbacks, the ocean circulation anomalies, the elevated solar output, a different kind of analytical tool was beginning to examine the dataset from a different angle entirely, and arriving at a finding that added a dimension of concern the physical models were not designed to detect. Part 14. AI models are flagging nonlinear climate behavior. Traditional climate models are built on physics. That sentence sounds straightforward, but its implications run deeper than they first appear, and understanding what it means and what it does not mean is essential for making sense of what a new generation of analytical tools is now finding in the climate data. Physics-based climate models divide the atmosphere, the ocean, and the land surface into a three-dimensional grid of cells, each one representing a volume of the Earth system perhaps 50 to 100 kilometers across horizontally and a few hundred meters deep vertically. To each of these cells, the model applies the equations that govern fluid dynamics, thermodynamics, radiation transfer, and atmospheric chemistry. It calculates the state of each cell at one moment in time, uses the governing equations to determine how that state will evolve over the next few minutes, updates all the cells accordingly, and then repeats the process, billions of times, step by step, to propagate a simulation of the Earth's climate system forward through months, years, decades, or centuries. The computational resources required to do this at high resolution are extraordinary. The largest climate modelling centres in the world run these simulations on supercomputers that perform quadrillions of calculations per second, and a single high-resolution global simulation covering a century of model time can take weeks of real-world computing time to complete. This is genuinely impressive science. It represents one of the most ambitious applications of computational modelling in human history, and it has produced projections that, in their broad directional assessments, have proven remarkably correct over the decades since the first generation of models was developed. But physics-based models have a characteristic that is built into their architecture at a fundamental level, and that characteristic becomes relevant when the system being modelled begins to behave in ways that the underlying physics equations were not derived to capture. The equations governing atmospheric fluid dynamics, ocean circulation, and radiative transfer were developed from observations of a climate system that, over the past several thousand years of the Holocene epoch, behaved with relative stability. The climate changed over that period. There were warm centuries and cold centuries, wet periods and dry periods, shifts in monsoon patterns and regional temperature distributions. But the system remained within a recognizable envelope. It did not undergo the kind of abrupt, large-magnitude transitions that the paleoclimate record shows, occurring in earlier periods of Earth history. The equations derived from this relatively stable system are continuous differential equations. They describe smooth, gradual change, where the state of the system at the next moment is a predictable function of the state at the current moment. They are optimized, by their mathematical nature, for representing systems that evolve continuously. They are not designed to predict discontinuities, moments when a system that has been changing gradually suddenly reorganizes into a qualitatively different state with different behavior, different equilibria, and different responses to forcing. These discontinuities have a name in dynamical systems theory. They are called tipping points, and the question of whether the Earth's climate system contains tipping points that could be triggered within the range of warming currently projected has become one of the most consequential and most unsettling questions in contemporary climate science. Machine learning models approach the same data from a fundamentally different direction, and understanding that difference is what makes the findings from these tools both potentially important and appropriately uncertain. A machine learning model does not encode physical equations. It does not assume that the relationships between variables follow the functional forms derived from fluid mechanics or thermodynamics. Instead, it ingests a large dataset. In the climate context, this typically means the historical observational record of temperatures, pressures, wind speeds, humidity, ice extent, ocean heat content, and other measured quantities, and identifies the statistical patterns and correlations present in that data without any prior assumptions about what those patterns should look like. It finds whatever structure exists, whether or not that structure conforms to the smooth, continuous behavior that physics-based models expect. This agnosticism about functional form is what makes machine learning potentially capable of detecting signals that physics-based models would miss. A pattern that precedes an abrupt transition, a subtle change in the variability or correlation structure of climate variables that occurs in the years or decades before the system crosses a threshold might not be predictable from physical equations calibrated on gradual behavior, but it might be detectable by a pattern recognition algorithm that has no prior commitment to smoothness. The algorithm does not care whether the transition is gradual or abrupt. It finds what is there. Several recent applications of machine learning to climate observational data have identified a pattern that researchers have described using various terms: nonlinear behavior, regime shifting, threshold dynamics, critical slowing down, that all point toward the same underlying concept. Certain climate variables, when examined over the full length of the observational record and extended into the recent anomalous period, do not show the smooth, gradually accelerating trends that a linear response to increasing greenhouse gas forcing would produce. Instead, they show periods of relative stability, years or decades during which the variable changes gradually and predictably, followed by transitions that are abrupt relative to the timescale of the forcing. The system appears to jump from one stable configuration to another, spending relatively little time in the intermediate states between them. This kind of behavior is characteristic of dynamical systems that have tipping points, and it is the kind of behavior that physics-based models, because of their mathematical architecture, are not well suited to predict in terms of timing, even when they can recognize the possibility in principle. The concept of critical slowing down is worth understanding because it is one of the theoretical signatures that machine learning approaches have been trained to detect. In dynamical systems theory, a system approaching a tipping point exhibits a characteristic change in its statistical behavior before the transition occurs. Its response to small perturbations becomes slower. It takes longer to return to its baseline state after being disturbed. Its variance increases. The fluctuations around the mean become larger. Its autocorrelation increases. The state of the system at one moment becomes more predictive of its state at the next moment, reflecting the sluggishness of the recovery dynamics. These statistical fingerprints of an approaching tipping point, sometimes collectively called early warning signals, can in principle be detected in the observational record before the transition itself occurs, giving a potential advance indicator of impending abrupt change. The challenge is that detecting these signals reliably requires long, high-quality data records, careful statistical analysis, and robust methods for distinguishing genuine early warning signals from the kind of low-frequency variability that can mimic them in short records. The methodology is still being developed. The validation record for these approaches in real-world climate applications is limited. Scientists working in this area are explicit about the uncertainty in their findings. None of this is settled science in the way that the physical attribution of greenhouse gas warming is settled science. What several groups working at the intersection of machine learning and climate science have reported, with appropriate caveats, is that certain observational datasets, particularly sea surface temperature variability patterns, atmospheric circulation indices, and polar ice extent records, are showing statistical characteristics that, when compared against the precursor signatures of abrupt transitions documented in paleoclimate proxy records, display elevated similarity scores compared to the same comparisons made against data from earlier decades. The current observational state of the climate system, in other words, looks statistically more like the period preceding a past abrupt transition than it looked 10 or 20 years ago. Paleoclimate data from ice cores extracted from Greenland and Antarctica, from marine sediment cores, and from cave formations called speleothems, provides a detailed record of past climate changes extending back hundreds of thousands of years. That record includes periods, most famously the Danskard-Ushger events of the last ice age, when Greenland temperatures changed by 10 degrees Celsius or more within decades. It includes the Younger Dryas, a period of rapid cooling followed by rapid warming that reshaped the climate of the entire northern hemisphere within timescales that, in geological terms, are nearly instantaneous. These abrupt transitions are real. Their mechanisms are debated, but their occurrence is documented in multiple independent proxies, and the machine learning work suggests that the statistical fingerprint of the current observational data is beginning to resemble, more than it previously did, the fingerprint of data that preceded those transitions. The limitations of this finding need to be stated as clearly as the finding itself. The machine learning models producing these assessments have not been peer-reviewed to the same standard as the physics-based projections that form the backbone of mainstream climate science. Their training datasets are limited in length and resolution. The relationship between statistical similarity to paleoclimate precursor patterns and the actual probability of an imminent abrupt transition is not quantified with the kind of precision that would allow it to be incorporated into policy-relevant risk assessments. Scientists working on these tools acknowledge all of this openly. The honest characterization of the current state of this research is that it is a developing field producing suggestive but not conclusive findings, that it warrants serious attention and continued development, and that its results should be held with the kind of calibrated uncertainty that the evidence actually supports, neither dismissed as noise nor elevated to certainty. But the signal is there, and the signal, if it reflects a real pattern, rather than a statistical artifact, is pointing toward a possibility that the physics-based models are not designed to quantify. That the climate system may be approaching a regime where the gradual, roughly linear response to greenhouse gas forcing that has characterized the observational record gives way to faster, less predictable, potentially self-sustaining shifts in the system's basic operating mode. The March heatwave, viewed through this analytical lens, is not simply an extreme event in a warming world that is otherwise behaving as expected. It is a data point in a pattern that the most pattern-sensitive tools available are beginning to flag as qualitatively different from the recent record. It is a reading on an instrument that was not designed to measure what it may be measuring, and if all of the threads this investigation has been pulling, the elevated baseline, the loading Pacific, the anomalous jet stream, the polar changes, the unaccounted forcings, the non-linear signals, if all of those threads are simultaneously real and simultaneously relevant, then the question that the entire architecture of this investigation has been building toward can no longer be deferred. What happens when the amplifier that was absent in March actually turns on? Part 15. What happens when the amplifier turns on? Let us go back to March. Denver hit 90 degrees on a day when 55 is the historical expectation. 30 red flag warnings activated simultaneously across the plains in a month when fire season is not supposed to exist. Temperature anomalies reached plus 20 to plus 30 degrees Fahrenheit above climatological averages across portions of the central United States. Anomalies that registered at 4, 5 and 6 sigma above normal depending on location. Values that a statistically stable system would not produce in 500 million years of observations. Soil moisture across the region sat at levels characteristic of late summer, not late winter. The jet stream was locked in an amplified ridge configuration that was unusual in its amplitude, unusual in its persistence, and unusual in the season in which it occurred. The land surface was behaving as though spring had never happened, redirecting solar energy into heat rather than evaporation because there was nothing left to evaporate. The heat dome that formed above it was not the origin of the event, but the amplifier of conditions that were already anomalous before it arrived. All of this occurred during a period when the equatorial Pacific was in a neutral to early transition state. La Niña had collapsed, faster than historical averages suggested it should. El Niño had not yet engaged. The primary global amplifier, the mechanism that historical records associate most reliably with severe warm anomalies in North American weather, was switched off. The March event happened without it. That single fact is the thread that ties every piece of this investigation together, from the soil moisture readings in Kansas to the subsurface heat measurements 300 meters below the Pacific surface, to the machine learning algorithms detecting nonlinear precursor signals in the observational record. That single fact is why the scientists who study this system were not merely impressed by what happened in March. They were quietly, seriously concerned about what comes next. And they had good reason to be. The scenario space for the remainder of 2026 branches in ways that depend primarily on what the Pacific Ocean decides to deliver, and the honest answer is that the Pacific has not yet decided. The subsurface heat reservoir is loaded. The precursor conditions for a significant El Niño event are present. But the precise strength and timing of that event, the degree to which the atmosphere and the ocean couple, the rate at which the thermocline heat rises to the surface, the extent to which the trade wind anomalies develop and sustain themselves, remains genuinely uncertain in ways that the most sophisticated models in the world cannot fully resolve months in advance. What the models can do is map the probability distribution of outcomes, and that distribution, in the spring of 2026, has a shape that deserves careful attention. The more moderate branch of the scenario space involves an El Niño that develops to the moderate strength range, above neutral, strong enough to shift atmospheric circulation patterns in recognizable ways, strong enough to tilt the odds toward a warm northern hemisphere winter of 2026 to 2027, but contained within the envelope of events that the climate system has produced multiple times in the modern observational record. Under this scenario, the summer of 2026 is hot. Measurably, significantly, record-challengingly hot. Drought conditions already established across portions of the central and southwestern United States deepen and expand. Fire season arrives earlier and runs harder and longer than any recent historical analogue suggests it should, drawing on the dry soil moisture baseline and the elevated temperatures to produce fire weather conditions that would have been considered extreme in July appearing routinely in May and June. The global mean temperature continues its record-breaking trajectory, adding another year to the sequence of historically unprecedented annual averages that has been accumulating since 2023. Agricultural systems already operating under stress face a season that pushes yield models into ranges they were not calibrated for. Public health infrastructure in heat-vulnerable regions faces demand that outstrips planning assumptions built on historical temperature distributions. It is a difficult year by any honest measure, a year that will produce real harm, real loss, and real evidence that the baseline has shifted in ways that require structural adaptation responses, not just emergency management ones. But it is also, under this scenario, a year that the systems of human society, strained, imperfect, inequitably distributed in their capacity to cope, have at least some framework for absorbing. because previous years have produced conditions in the same general range and the institutions that respond to climate extremes have some operational experience to draw on. The more aggressive branch is where the scenario space becomes harder to describe without using language that sounds alarmist but is in fact simply accurate. This branch involves an El Niño that develops toward the strong or very strong end of the model distribution, the tail scenario that the subsurface heat content data makes physically plausible without making it certain. Under this scenario, the summer of 2026 produces temperature and drought anomalies that exceed the historical planning envelope, not the planning envelope built on old historical averages, but the revised planning envelope that emergency managers and agricultural planners have been updating in response to recent years of above-normal conditions. The fall and winter of 2026 to 2027 brings a global temperature spike that, layered on top of the already elevated baseline, produces the highest annual mean global surface temperature in the instrumental record by a margin large enough to be unambiguous. Marine heat waves intensify across multiple ocean basins simultaneously, pushing coral reef systems that survived the 2023 and 2024 bleaching events into conditions that leave less room for recovery between events. Monsoon systems across South and Southeast Asia, the precipitation patterns that supply fresh water to roughly 3 billion people and support some of the most productive agricultural regions on Earth, are disrupted in ways that models consistently characterize as negative for agricultural output, even when they cannot agree on the precise regional expression of the disruption. The Antarctic sea ice, already failing to recover across multiple consecutive seasonal cycles, remains at suppressed extents, removing additional albedo from the Southern Hemisphere energy budget and adding incrementally but continuously to the warming commitment. The forcings stack, the anomalies compound. The tail scenario is not an apocalypse. It is a year that reorganizes the risk landscape in ways that make the subsequent decade demonstrably more dangerous than the decade that preceded it. The concept of compound events is where the risk analysis becomes most sobering, and it is the concept that the emergency management and climate adaptation communities have been working hardest to incorporate into planning frameworks that were historically built around individual extreme events occurring in isolation. A heat wave is damaging, a drought is damaging, a severe fire season is damaging. Each of these events, occurring alone, can be characterized, planned for, responded to, and recovered from within the operational capabilities of the systems designed to handle them, imperfectly, unequally, with real costs, but within the envelope of manageable response. Compound events are categorically different, a drought occurring simultaneously with record heat, in a region that entered the season with already depleted soil moisture and below normal snowpack, under atmospheric conditions that sustain fire weather through a season that begins earlier and ends later than historical norms. That is not three separate stresses being added together. It is three stresses interacting multiplicatively, each one making the others worse, each one consuming the resources and reducing the resilience available to respond to the next. The agricultural system facing simultaneous heat stress, water stress, and smoke impacts on photosynthesis is not experiencing the sum of three moderate stresses. It is experiencing a qualitatively different kind of failure. Infrastructure systems designed with redundancy sufficient for one extreme at a time become inadequate when multiple extremes arrive in the same season. The risk multiplication from compound events is real, documented, and currently underrepresented in the planning frameworks of most institutions that bear responsibility for responding to climate extremes. The uncertainty in this picture is honest, and it is important, and it needs to be held clearly alongside the concern. The tail scenarios are possibilities existing within a probability distribution, not certainties written in any physical law. The subsurface heat content of the Pacific is a precondition for a very strong El Niño, not a guarantee of one. A full fuel tank does not guarantee a car accident. It establishes the conditions under which an accident would be consequential. The climate system retains genuine variability. The atmosphere can produce surprises in directions that reduce the outcome rather than amplify it. Forecasters who correctly predicted that March would be anomalously warm still underestimated the magnitude of what arrived. That epistemological humility is not a reason for complacency. It is a reminder that uncertainty runs in both directions, and the direction it has been running in recent years is consistently toward outcomes more extreme than the central projection. The honest characterization of the probability distribution for 2026 is that it runs from serious and significantly above historical norms at the low end to historically unprecedented across multiple interacting systems simultaneously at the high end, and that the physical state of the climate system in early spring of 2026 places more probability mass toward the serious end of that range than any previous year in the observational record. 2026 sits at an intersection of forcing factors that has not previously existed in the instrumental era. The background warming trend has elevated the baseline to a level where March is producing June weather without any additional amplification. The Pacific is carrying a subsurface heat reservoir that has not yet discharged into the atmosphere. The jet stream is exhibiting behavior consistent with a structural weakening that makes persistent extreme events more frequent and more prolonged. The polar systems are losing the stability and the reflectivity that have historically moderated heat absorption at high latitudes. The sun is delivering slightly more energy than the models calibrated on a week cycle forecast assumed. The land surface is entering spring drier than at any point in recent memory, and the phantom forcings, the aerosol reductions, the cloud feedbacks, the ocean circulation changes may be operating at the more aggressive end of their plausible ranges in ways that the model ensemble is not yet fully incorporated. All of these factors were present and operating simultaneously when Denver hit 90 degrees in March without El Niño's assistance. We have always thought of extreme weather events as the system behaving badly. But what if the system is not misbehaving? What if it is operating exactly as physics predicts it would at this level of forcing, and what we are calling anomalies are simply the new operating range? What if March 2026 is not the worst chapter of this year, but the quietest one, the baseline reading taken before the instrument range expands? We are not reacting to a heat wave. We are watching the system finish warming up before the main event begins. The amplifier is loading, the Pacific is charging, the baseline is elevated, and the question that every thermometer, every ocean float, every satellite sensor, every ice core, and every pattern recognition algorithm is asking simultaneously in the spring of 2026 is the same question it has always been, stated now with a new and uncomfortable urgency. We are ready for what the climate system has already delivered. The question is whether we are ready for what it is preparing to deliver next.